Hi all, welcome to Heights to Fly. In previous class, we discussed about Euclid's division lemma, how to find HCF, some proofs related to Euclid's division lemma, etc. Today class we are discussing about fundamental theorem of arithmetic. The theorem states that every composite number can be expressed as a product of primes. And this factorization is unique apart from the order in which the prime factors occurs. Once again, every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. First of all, we have to discuss about what is a prime number. Prime number is a number which have only factors as 1 and that particular number. For example, 5. 5 have factors 1 and 5 only. 7 have factors 1 and 7. But 8 is not a prime number, because it have factors 1, 2, 4 and 8. So 5 and 7 are prime numbers, but it is not. And similarly, next case is 13. What is 13 is a prime number or not? 13 is a prime number because it have no other factors other than 1 and 13. Okay. Then let's go to the theorem. Every composite number, consider a number (28). We can express it as a product of primes. We can factorize it to 28 divided by 2, we get 14. Again 2, we get 7. So we can represent it as 2 into 2 into 7. 2 is a prime number, 7 is a prime number. So what is the theorem? Every composite number, this is a composite number, every composite number can be expressed as a product of primes, and this factorization is unique. This factorization is unique apart from the order. Order means we can factorize 28 again as 7. We get 4, 2, 2. That is the order. 2 into 2 into 7 is similar to 7 into 7 into 2. That is the theorem. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. And let's go to another example. Consider the example 32760. Let's go to the factorization. Divided by 2 will result 16380. Divided by 2 results 8190. Divided by 2 results 4095. Divided by 3 results 1365. Divided by 3, 4. So it's 455. Divided by 5 results 91. Divided by 7 results 13. So we can represent this number in a tree form. Here the first factor is 2, and dividing by 2 we get a value 16380. Again 2, (8190) divided by 3 results as divided by 8,120 divided by 2 results 4095. 3 results in 1365 divided by 3 results in 455 divided by 5 results in 91 and 7 results in 13. So this is the factorization tree. Here we get the factors. So 32760 can be expressed as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Okay, this is the factorization method. Let's go to the application problems relating this fundamental theorem of arithmetic or factorization. First question is, find LCM and HCF of 6 and 20. Find LCM and HCF of 6 and 20 by prime factorization method. By prime factorization method. So 6 and 20 are the numbers. We can factorize the value 6 as 2 into 3 and 20 as 2, 10, 2, 5. 2 into 2 into 5. You can rewrite this as 2 square into 5 raised to 1. 6 as 2 raised to 1 into 3 raised to 1. Then what is HCF? Highest common factor of 6 and 20. Highest common factor of 6 and 20. We can take HCF by using this rule. HCF is the product of smallest power of each common prime factor in the numbers. What is HCF? Is the product of smallest power of each common prime factor in the numbers. Each common prime factors. Here the numbers included in factors are 2, 3 and 5. Which value is common? 2 is present in both cases. Here 2 is present, here 2 is present, but 3 is not present in both cases. Here 3 is only present in 6, 3 is not present in 20. So we can't take 3. We can't take 3. Common, each common prime factors. And another value is 5. 5 is not present here, only present here. So we can't take 5. Only we can take value 2. So the common value is 2. In both cases 2 is present, and the second condition is smallest power. Second condition is smallest power. This is smallest power. 2 raised to 1 or 2 square. 2 raised to 1 is the smallest power. So the result is 2. Once again, highest common factor is find out by product of smallest power of each common prime factors. Here the common prime factor included in both cases is only 2, and smallest power is 2 raised to 1 or 2 square. 2 raised to 1, so the value is 2 raised to 2. Next is LCM, least common multiple of 6 and 20. 6 and 20. LCM is find out by product of greatest power of each prime factor. Product of greatest power of each prime factor. Product of greatest of each prime factors include 2, 3 and 5. There is no doubt for that. Greatest power. If 2 has the greatest power in 20, that is 2 square. 3 has the greatest power. There is no condition like common. Greatest power of each prime factor. So we have to take 3 also. Greatest power is 3 raised to 1 and 5 is 5 raised to 1. So the value is 60. So we get least common multiple as 60. HCF is 2. Next, another statement we are discussing is, or an equation, HCF of A comma B into LCM of A comma B is equal to A into B. HCF of A comma B into LCM of A comma B is equal to A into B. Here A and B are 6 and 20. 6 into 20 is equal to HCF of 6 comma 20 is equal to 2 into 60. And the value is 120. Value is 120. So when we get two numbers, when we multiply it, the result is same as HCM and LCM of product of LCM and HCF of these two numbers. Don't forget the condition. A into B, two numbers, product of these two numbers will be equal to the product of HCF and LCM of these two numbers. Okay. Next, we are going to another example. Find LCM and HCF of 96 and 404. Go to the factorization. When factorize 96, we get 48, 2, 24, 2, 12, 2, 6, 2, 3. So we can represent it as 2 into 2 into 2 into 2 into 2 into 3. 1, 2, 3, 4, 5. So 2 raised to 5 into 3. The next number 404, factorization 2, 202, 2, 101. For 101, there is no other factor. This is a prime number, so we can represent it as 2 into 2 into 101 is equal to 4 into 101. 2 square into 101. LCM and HCF. HCF, smallest power of HCF, smallest power of each common prime factor. Common prime factor. Here the common prime factor is, factors are 2, 3 and 101. Here the smallest power is 2 square, which is equal to 4. To find out LCM, the greatest power of each prime factor. For 2, the greatest power is 2 raised to 5, 3 into 101, which is equal to 2 raised to 5 is equal to 32, 3 into 9696. HCF, LCM. Okay, so HCF is the smallest common power factor, prime factor, and LCM greatest factor. Okay, then let's go to the equation that's been discussed. LCM into each other. The numbers are 96 into 404, which is equal to, what is LCM into HCF. LCM into HCF means 9696 into 4. Here we proved A into B is equal to LCM of A comma B into HCF of A comma B. Let's go to another problem. find LCM and HCF of 6, 72 and 120. 6, 72 and 120. By factorization we get the result as 2 into 3, 2 raised to 1 into 3 raised to 1. 72, 2 raised to 3 into 3 square. 120, 260, 230, 215, 3, 5. So 2 raised to 3 into 3 into 5. Then what is HCF of these three numbers? The smallest common factor, smallest. Here 2 raised to 1, 3, 3 raised to 1, 5 is not common in this case. So the result is 6. LCM, greatest common factor. So 2 raised to 3 into 3 square into 5, which is equal to 8 into 9 into 5, which is equal to 360. 360. Let's go to another example, which is a proof related problem. It is example 5 in the NCERT CBSE textbook. Example number 5 in the textbook, first chapter. And the question is, consider the numbers 4 raised to n. Consider the numbers 4 raised to n, where n is a natural number. Check whether there is any value of n for which 4 raised to n ends with the digit 0. Check whether there is any value of n for which 4 raised to n ends with a digit 0. Once again the question, consider the numbers 4 raised to n where n is a natural number. Check whether there is any value of n for which 4 raised to n ends with the digit 0. Consider solution. Let's go to the solution. Consider the number 4 raised to n for any n. For any n ends with the digit 0. According to the prime factorization method, if it ends with 0, it would contain a prime number 5 in factors. If it ends in 0, you know that how to find out the factors of 5. Either it will ends in 5 or it will ends in 0. So a number which ends in 0 should contain 5 as a factor. So when 4 raised to n ends with 0, we can say that it should contain a prime factor 5 as factor. But when we represent 4 raised to 10, can rewrite it as 2 raised to 2n. So the factor is 2 only. According to the prime factor fundamental theorem of arithmetic, there is no other prime factor other than 2. There is no other prime factor. Once again, consider the number for 4 raised to n where n is an integer. According to prime factorization method, it ends with it. In the question itself, it says that it ends with 0. When it ends with 0, it should contain a 5 as a prime factor. But when we rewrite the equation as 2 raised to 2n, the factor only contains is 2, no other prime factor. So 5 is not a factor. So we can say that it should not ends in 5. It should not ends with the digit 0. It should not, hence it should not ends with digit 0. Once again, the important statement here is when a number ends with 0, it should contain 5 as a prime factor. Should contain 5 as a prime factor, but when we consider 4 raised to n, it have only factor 2. So we can say that it should not, the number 4 raised to n should not ends with the digit 0. Okay, today we discuss about fundamental theorem of arithmetic. Fundamental theorem of arithmetic, and it relates to the composite number can be represented as product of primes, and some of the problems like LCM and HCF, how to find LCM and HCF, and another equation related to LCM and HCF, that is the product of two numbers, can be represented as again using HCF and LCM, which is equal product of two numbers is equal to product of HCF and LCM of that numbers. And another 2-3 examples. So on next class we will discuss about more problems on fundamental theorem of arithmetic that included in the textbook as exercise. So thank you for watching. Thank you for watching. Please subscribe and share for new videos.